Hey Algebra 2, here are your notes for 7.3 talking about square root functions. So before we jump into 7.3, let's jump into 7.2 review. So will the following functions have inverse functions? If you remember from our last video, inverse functions are ones that are mirrored over the identity function, y equals x, over this line here. So in theory, if I mirror each of these over and they still create a function, then we do in fact have an inverse. However, if we mirror it and it turns out to not be a function, that's when we can't say that we have an inverse function because it doesn't follow the rules that a function needs to. So this one, I've drawn that identity function, and now I'm just going to do a really light, easy sketch of what this looks like mirrored. So this part would mirror over. It would look something like that. This part would mirror over to here, and it's a straight line, so it should look something like that. Now, obviously, that's not perfect in any way, but I do notice that 0, 2 becomes 2, 0. So that's just a reminder that that follows our x becomes y and y becomes x. That was a giveaway from our last video to know that it had an inverse. So based on this, how do I know it's a function? Well, this we have to go back to semester 1-4. This is that vertical line test. This new function, this new line that we have still has to follow the vertical line test. Now, if we check, it does. So this one, when we create its inverse, we check that the vertical line test works, and once we see it works, we see it is in fact a function. Let's do the same thing with the next one. Again, I'm just going to sketch in that identity function because I know that I'm going to have to mirror over to get my inverse. And now I can already tell you, mainly because that color won't work, that when I rotate this or when I transform it as a mirror image, this is going to cause some issues. It probably isn't going to pass that vertical line test. So I'm going to do this one in orange. Let's see how it looks. Again, this is just a sketch, so please know that it's not going to look good or perfect by any means. It's probably going to look something like that. That piece is going to be mirrored over as well. And it's going to come kind of like that. That's a general sketch of what that should look like. So now immediately we should be able to see that once we take the inverse, that inverse does not pass the vertical line test. It breaks it right away. So while this one has an inverse, it does not have an inverse function. And then the last one. The last one I think is probably the easiest to see because there's your identity function. And if we mirror this over, it's going to look something like that. It still obviously passed the vertical line test, so that one's good to go. All right, let's jump into 7.3 now with the square root functions. So if a function contains a square root of a variable, it is called a square root function. The parent function of the family of square root functions is y equal to the square root of x. Now, this is just a good parent graph to log away because we do use square roots pretty often. And of course, it says use the coordinate plane to the right to graph the parent function. Now, in working with this, I've started to just see what it looks like, but if you're just starting out, obviously we always start with a table. And the biggest hint that I can give you is that because we know square roots are a little tricky, let's pick nice numbers to plug in for x that we know will give us a nice number for y. So first off, 0. Square root of 0 is 0. That's a nice one. 1. Square root of 1 is 1. That's a nice one. However, when we go to plug in 2, we get the square root of 2. Now, while we could approximate it, I don't really like working with the calculator any more than I have to. So I'm going to skip 2. I'm going to skip 3. But I know that the square root of 4 is nice with 2. And then I know the next nice perfect square would be 9, and it would give me 3. So try to pick numbers that work when you're doing a table. If you can think through that, that'll really help you. If you can't, feel free to approximate and plug it in the calculator. Just a little extra time, no big deal. All right, now let's take that table over and graph it. 0, 0, 1, 1. This starts out nicely. However, once we have to go over to 4, 2 and 9, 3, and we connect the dots, you're going to see that it kind of makes this up, up, and away pattern going off to the right. So that is your basic, most basic parent function for y equals the square root of x. And this is one of the most important things you should be able to sketch, I would say, going forward. So now let's take that and let's graph some variations, some transformations of that parent function, and talk about how they relate to graphing that we've already done. Well, this first one, I would say you can create a table for these, or you can go to Desmos and see what they look like. I'm going to tell you what they end up being graphed as, and I'm going to show you those connections. So if you remember from our graphing unit, things that were inside of parentheses, we always remember you can't trust the inside man. So the inside man was always opposite the sign, and it always moved us horizontally. So this positive 4 inside of my square root, because it's all the way in the square root, is going to be a horizontal transformation of negative 4. If you don't remember those tips and tricks that I reminded you of, no big deal. You're going to relearn them now. So, horizontal transformation of negative 4. What that means is that where we usually have 0, it's going to transform that back, negative 4. So instead of starting at 0, 0, I'm going to start at negative 4, 0. Instead of starting at 1, 1, I'm going to transfer that back to negative 3, 1. Instead of having a point at 4, 2, I'm going to have a point at 0, 2. And then instead of at 9, 3, it's going to be at 5, 3. Because all I've done is shift this graph back 4 units. So then how does it differ when the 4 is outside? Well, if this was a horizontal shift of negative 4, because it's on the inside, the horrible horizontals, horrible inside guy, it would make sense that outside would be a vertical shift. And vertical, you can trust the outside guy. He's not on the inside. He's not the, how did I put it before? The double spy. He's not spying for both teams. So we can trust him and say that he is a positive 4. So if we go back to our parent graph, we used to have one at 0, 0. Now we are shifting up positive 4 vertically. So we're going to start here. Instead of at 1, 1, now we're going to be at 1, 5. Instead of at 4, 2, we're going to be at, let's find 4, 2, there we go. We're going to be at 4, 6, and then so on and so forth. Did I miss one? Nope, we're good. There we go. And then, of course, we just connect those dots. So notice, this was a vertical shift of plus 4. And I always come up with silly things to remember these. However you want to remember them is fine. You should just remember that the difference between a horizontal and a vertical. All right, this one's getting a little tricky. We've got multiple things going on, and we've added a number out front. So let's talk about what each of those does. We're used to the inside. That's the first one we saw. Remember, horrible horizontals. It's going to do the opposite of what we think. So this is a horizontal, but instead of going negative 3, it's going to go positive 3. The outside one was our second example. That is a vertical. It's very trustworthy vertical, so it's going to do exactly what it says. It's going to go plus 1. But then we have to also take into account this 2 out front. What is a 2 going to do to this entire function? Well, let's think about it. If we plug something in here, we're going to be multiplying it by 2. That multiplication is essentially going to take your function and it's going to stretch it and make it much bigger. So this is going to be a vertical stretch upwards. So this is going to be a stretch, and I just say upwards because it's a positive number. It's making it bigger. If it was a fraction, if it was less than 0, it would be stretching it, but it'd be smaller. It'd be shrinking towards the x-axis. So let's take all of this into account. It's a horizontal shift of +3. So instead of starting at 0, 0, we're going to start over here. Instead of starting here, it's a vertical shift of +1. So I'm going to go up 1. And then that 2 out in front, when it's out in front, it's a nice, I don't know how to say it, it's a nice stretch. So our second dot, where it would usually be, it's kind of hard to explain, but in a normal graph, it would be right here. See how each dot is 1 box away? Well, in this one, it's going to stretch it. It's going to make it a little bit taller. So this one is actually going to have its dot not at 1 away, but it's going to be at 4, 3. 4, 3. It's going to stretch it up by a factor of 2. Same thing with our other dots. Instead of being 3 away and 1 up, we're now going to be 3 away and 2 up. Instead of being 9 away and 3 up here, we're still going to be 9 away, but we're going to be 6 up. So this is eventually going to stretch out significantly, whereas these ones are a little more flat. This one's a little bit taller. So hopefully that makes sense. And then this would come down a little bit too, but that's a general sketch. I'm not looking for perfection here. I'm looking for a few things. I'm looking that you recognize what each of these adjustments does, generally speaking, and I'm looking for your ability to sketch this general shape. Remember when we were learning quadratics, we were sketching a general shape. If you have to make a table to do that, totally fine. I'm not going to be super hardcore on that, but you should know the general idea. All right, and the last one I want to talk about is this weird one, this 3x minus 4. You'll notice in comparison to the last one we were looking at, we now have a 3 on the inside. This 3 is still a vertical shift, but it's not quite as nice. Where this one bounced our box up by a full factor of 2, this one doesn't quite do that. It's a little bit harder to explain. And this is where that sketching aspect comes in. Let's first take this 4 into account. That's a horizontal shift of +4. So I'm right away going to just go ahead and change my dot. Once I'm there, however, that 3 still causes some issues. It actually slightly adjusts where the dot starts. So for this one, I suggest if you have a number inside, regardless of the other transformations you're doing, you put this one in a table. Now, I've already done this. I know that I can't go any lower than what would give me a -4 in there because it wouldn't exist. And I'm just going to start plugging in numbers. When I plug in 2, I get out 1.4. When I plug in 3, I get out 2.2. And when I plug in 4, I get out 2.8. No matter what I plug in here, I'm not going to get nice stuff. So unfortunately, this is one of those ones where if you have a number inside, you can't do anything but check the calculator. 3 goes to 2.2. 4 actually goes to 2.8. Now, if we had been listening to our horizontal shift, that is where it should have started. However, this shift inside is so problematic that it actually shifted our position back here. It started a little bit differently. So again, check the calculator on that one. All right, now I have just a quick box, I think. I don't know, it's a key. If you have something in a square root form like this, an adjustment to A is going to be a nice vertical stretch. It sounds like when you put your hands over your head and stretch your back out. That's a nice vertical stretch, good for the back muscles. However, when you adjust B, it's also a vertical stretch, but it's not quite as nice. So that one is a vertical stretch, and I'm going to say plus calculator. And then the adjustments to H and K we just talked about. An adjustment to H is a horizontal shift. And remember, it is opposite sign. So if there's a negative, we make it positive. If there's a positive, we make it negative. And then finally an adjustment to k. K is always the one on the back side. He's always the one outside of the square root. He's going to be our vertical shift, not our stretch, our vertical shift. And he is the same sign. We don't change him. He's a very trustworthy sign. So same sign is given. So there you go. Now let's take this and let's actually apply it a little bit. So a lookout on a sub is h feet above the surface of the water. The greatest distance d in miles that the lookout can see on a clear day is given by the following. And then graph the function. Right away, you guys know how I prefer to just pull out the numbers of a problem. I don't like working with all of the extra words if I don't need to. So there's my function that I'm working with. And it doesn't ask me for any information that has to do with the problem. All it says is graph it and state the domain and range. So that's what I'm going to do. I'm not even going to pay attention to the rest of the words. I've said this 1,000 times in my other videos. Don't get overwhelmed by word problems. They are just a lot of extra that we don't necessarily need. So make sure you look for what the problem's asking for and disregard the rest. All right. The only problem is right away I see that nasty inside vertical stretch, that I just don't like. So I'm immediately going to go to a table. When I plug in h, what do I get out for d? And then let's just start plugging in numbers. If I plug in 0 for h, I get 3/2 of 0, which is 0. Square root of 0 is 0. If I plug in 1, I'm going to get 3/2 times 1, and then I'm going to have to take the square root of 3/2. When I plug that into my calculator, I get about 1.2, roughly. That's a lot bigger decimal, but that's what I'm going to leave it with for right now. All right, when I plug in 2, I get 3/2 times 2. It's just 3. But then I have the square root of 3, which I have to put into my calculator. When I calculate that, it's about 1.7, approximately. And I could keep going to see what's going on here, but these 3 points are going to be enough for now. All right, I've got 0, 0. We're working on a pretty small scale here. So I'm actually going to go up and put 1 here. And I'm going to put 2 here. That gives me a few more boxes to work with. So 0, 0, when I go, I guess I have to do that in this form too. So 1, 2. Okay, so 1 goes up to 1.2, which is about here. 2 goes up to 1.7, which is about here. And I'm going to stretch that graph. Obviously, if we had made it much smaller, it would have been much harder to see, so I personally just prefer the way that looks. You can make it a much smaller graph if you prefer. However, we're not done here. A lot of you like to forget that it says state the domain and range. You're so afraid of domain and range, but don't be. Remember, domain is just how far left and right can we go. If I put my pen in the middle of this function and I go to the left, how far can my pen go before I am forced to stop, before I hit the end of my function or some other boundary? Well, because this can't keep going, we can't have a negative square root. My domain goes from 0 on the left over to what? Well, this arrow on the end of my square root function indicates that's going to keep going forever. So at this point, it sure does look like my domain can go from 0 all the way to positive infinity. And that's with the inequality symbols. You may also prefer it with the parentheses and the brackets. I know some of you prefer that. Same thing for range. All we want to know is if domain was left and right, range is going to be up and down. If I put my pen in the middle, how far down can I go? What is the least value my pen can hit before I'm stopped by that boundary? Well, in the y direction, it's going to be 0 as well. Now, when I go up, it sure looks like this levels off. However, I'm going to tell you that square root continues to go up. It's still making forward progress in the upward direction as well. So this range is actually going to be the same as my domain. Just like that. All right, let's keep going. A ship is 3 miles from a submarine. How inconvenient. That does not appear to be on either of my axes here. It says, how high would the submarine have to raise its periscope in order to see the ship? Well, this is kind of tricky, but I do know I'm still going to need this function. I'm still going to need d equals 3/2 h. But it also gives me some more information. It says a ship is 3 miles from a submarine. But I don't know if that's d or h yet, so let's go back to our original problem and see what it says. It says the lookout is h feet, so the lookout itself above the water is this h. And then it says the greatest distance in miles that the lookout can see is given by this. It says a ship is 3 miles from a submarine. That is a distance from our submarine to our ship, not from our submarine to our ship. The ship isn't flying up in the air. So I can already tell you, since that 3 miles is a distance, my d is going to be 3 miles. And then it says how high, aka height, would the submarine have to raise its periscope in order to see the ship? That tells me that I'm looking for my height. From here, it's just a plug and chug operation. There we go. So 3 equals the square root of 3/2 h. Now it's just solving for a square, solving to get rid of that square root. Excuse me. So how do we get rid of a square root to get that h by itself? Easiest way, square both sides. Squaring both sides gets rid of the square root on that side. It makes this a positive 9. So I now have 3/2 h equals 9. How do I get rid of a fraction? I multiply by the reciprocal. And I'm left with h. I'm going to put the h on the left side. It's a variable thing. And then 9 times 2/3 is 6. So how high would the submarine have to raise its periscope in order to see the ship? We know that h is in terms of feet. So it would have to raise its periscope approximately 6 feet. All right, last one. I know I've thrown a lot at you. Stay with me just a little bit longer. So how do you think the graphing process changes when we have an inequality versus an equality? Well, the process stays basically the same. We're still going to graph it in the same way. However, just like when we graphed other inequalities earlier in the semester, we have a few extra steps. So, I'm just pulling one thing up here. First, we're going to do our basic sketch. So a basic sketch of this graph. I've got a 2. That's one of the not as nice transformations. I've got that 6, but as soon as I see that 2, I know I'm going to have to make a table. So I'm just going to go over and do that right away. I've got x, I've got f of x. Let's start plugging in numbers. If I plug in a 0 right away, I'm going to see that -6, not going to work. I'm going to have the square root of -6. I'm going to have an imaginary number. The first number I could possibly put in where I would not have a negative is the number 3. Because when I plug 3 in for x, I get 6 minus 6 is 0. Square root of 0 is 0. So 3 is a nice one. From there, I'm just going to start putting in numbers because that's the lowest I can go, so I know I can definitely go higher. All right, throw in 4. When I put in 4, I get 8 minus 6 is the square root of 2. I believe I did that a minute ago, but let me recalculate. 1.4. Plug in 5. That would be 2 times 5 is 10. 10 minus 6 is 4. That's a nice one. We got lucky there. That's 2. And now I have about 3 points. 4 is better, but I'm going to stick with 3 for now. All right, 3, 0, 4, 1.4. It's about there-ish. And then 5 goes up to 2. So it looks something like that. And then I think my next one would be over here-ish approximately. However, I don't want to fill in this line right away. I want to check the boundary. And hopefully we remember which of our signs gives us which boundaries. So if I have a less than or greater than sign with no line underneath, that's going to be a dashed boundary. If I have the less than or equal to or greater than or equal to, that is where I have a solid boundary. So if we go back up and check our function, I only have the less than, meaning it is a dotted boundary. So I'm going to go ahead and put in the dashes there. And then, of course, arrow on the end. And then the last thing, because this is inequality, there is some shading involved. And how do we decide which side we're going to shade? Well, we have to check a point, just like we did before. I like to check a point that's rather close. Checking 0, 0 doesn't make sense to me because it's all the way over here. But let's check something like, I guess something that would come out nicely would be nice too, but I can't think of anything off the top of my head. Let's plug in 8, 1, just because I can see it over here. I'm going to plug that into my original function. So 1 is less than the square root of 2 times 8 minus 6. Let's check this. 2 times 8 is 16. 16 minus 6 is 10. This is square root 10 greater than 1. I don't necessarily know off the top of my head, but I can tell you that the square root of 9 is equal to 3. And I know that the square root of 10 is bigger than the square root of 9. So is 1 less than 3? Yeah, it is. This is just an approximation. You can also throw that in a calculator to check. But that's my fast, simple way of doing it. And then, of course, there's always Desmos if you want to check it that way. So anything below this line and to the right of this boundary, because that's our domain says we can't go any further, can be shaded. So I'm just going to go ahead and shade it in. And yes, I can shade below that line because it just says less than. That includes imaginary numbers as well as real numbers. So don't hesitate to go below the axis on that one. All right, I know I threw a ton at you. Thank you for sitting with me. If you have any questions, please don't hesitate to let me know.